All right, so we're going to start with gravimetric stoich. There's 3 different types, and all you have to do is apply the same exact process and thought process to each type to get what we're looking for. So the easiest little analogy for stoichiometry is thinking about s'mores. When we make a s'more, we take 1 marshmallow, 1 piece of chocolate, and 2 crackers to make 1 s'more. So if I have 9 crackers and 6 marshmallows, we all know that we can only make 4 s'mores because we're limited by the number of crackers. So 9 crackers and 6 marshmallows, we can only make 4. Because of this ratio that 1 s'more requires 2 graham crackers. So it's all about ratios and remembering that we have to convert between the ratios. So just because we had 9 crackers doesn't mean that we can make 9 s'mores. Okay, so stoichiometry is just that. It's a method of predicting the quantity of a reactant, so how many things we need to make our s'more, or our product, so how many s'mores we need, but in a chemical reaction based on the quantity of another reactant or product in that same reaction. So just like we're making our grocery list for s'mores, we can do that with chem. Gravimetric stoich is stoichiometric analysis involving masses. So gravimetric meaning mass. So when we're measuring things, we don't actually get to measure moles. We're measuring mass. We all know this. So with our scales, we measure mass, and we can convert that always, as long as we know what it is, into moles. So gravimetric stoich has a few different steps, and the steps are going to be very, very similar to every type of stoichiometry we do. First and foremost, every time you must write out a balanced equation. You will be searching in the dark for a right answer if you don't have a balanced equation. We're going to use those coefficients like we did in our dissociations. Next, we're going to write out the information given in the question below the appropriate compound. So if we get information about one of the reactants, we're going to write out its mass below it, and we're also going to calculate the molar masses for substances that we are involved with in this question. So we can calculate molar masses for the known, which is something that we're given information about, so the mass. The molar mass of the unknown. Unknowns are things that we're asked or required to find information about. After we write out what we know, we're going to calculate the number of moles of that known chemical using its molar mass and the equation N is equal to little m over big M. Once we have moles of that known, we can convert it into the moles of the required or unknown substance using the mole ratio from the coefficients of the balanced equation. So what we're going to do is we're going to have moles of our known, and we will cancel moles of known on the bottom of one fraction, and we're looking for moles of our unknown so that we can solve for it. This will give us moles of our unknown because moles of known will cancel. The mole ratio is just this, unknown over known. It's the ratio between the molar amounts of any 2 elements or ions or compounds in an equation. All right, it's identical to the coefficient in the equation. In all stoichiometry calculations, the 4th step is the same. The mole ratio is used with the coefficient for the unknown substance in the numerator, and the coefficient for the given substance is in the denominator, just like what I've written up there. Then once we've got moles of our required substance or our unknown, we can convert that into a mass using its molar mass and the equation M is equal to little m times big M. Note, do not round until the final answer, okay? Remember to keep unrounded values in your calculator or at least a couple extra sig figs throughout. Otherwise, you're going to make an error too early. So, best way to do this is to practice. Let's get one question. Alright, so when the oxygen in air reacts with iron, rust or iron 3 oxide is formed. What mass of oxygen is used for every 100 grams of rust formed? So in writing our balanced equation, we're going to get iron as a solid and oxygen, which is O2, don't forget, as a gas makes iron 3, which is Fe2O3 when we drop and cross our charges. To balance this, looking at oxygens here, we have 2 oxygens on this side and 3 here. So what we're going to need to do is double this And with that, now we have 6 oxygens, so we have 3 O2s. I don't know what's up with my pen here, guys, sorry. And we have 4 irons. Excellent. Writing what we know about each thing below it, we get 100 grams of rust, and we're looking for the mass of oxygen. So, because we have mass and we're looking for moles or vice versa, what we're going to get is we need to find our molar mass for each of these. So calculating those, we're going to get 159.70 grams per mole for iron 3 oxide. And of course, our molar mass for oxygen should be 32.00 grams per mole. All right. So first step is done. We had our balanced equation. Now we've got our information written below. Step 3 is to find the number of moles of our known. So our known is one that we can calculate the moles of, and that's our iron 3 oxide here. The unknown is what we're looking for. So our unknown is our oxygen. So to calculate moles of our known, we're going to go N is equal to little m over big M, which is equal to 100 grams divided by 159.70 grams per mole. And I do believe we got 0.6262 moles. So in the end, I'm going to get 3 sig figs. So I'm going to keep 3 throughout my work here. All right, and that's moles of Fe2O3. So next, we're going to convert moles of Fe2O3 into moles of oxygen, and that's using our mole ratio. So 0.6262 moles of Fe2O3. And we need to cancel moles of Fe2O3. So we're going to put those on the bottom. Moles of Fe2O3. And we're trying to find moles of oxygen. So that's going to go on top. Now these come from our coefficients here. So 3 moles of oxygen in our balanced equation per 2 moles of iron 3 oxide. And when we multiply across and divide by everything across the bottom, we get 0.9393 moles of oxygen. So from moles of oxygen, now we can go ahead and find our mass of oxygen. So mass of oxygen will be N times big M. So 0.9393 moles times 32.00 grams per mole. And what we get is 30.1 grams. All right, so it takes 30.1 grams of oxygen to make 100 grams of iron 3 oxide. Awesome. All right, in our next example here, what we're going to do is we are going to have copper 2 sulfate is reacted with 15 grams of sulfur. What mass of free copper is produced? So we are going to start once again with that balanced chemical equation. So copper 2 sulfate, so CuSO4, and that's likely going to be aqueous. Sorry, I didn't note it. Solution is reacting with silver. So silver is a solid by itself, no charge. And we're going to make copper solid and Ag2SO4. That's likely going to be a solid as well, actually. All right, balancing. We're going to need 2 silvers over here. And that looks like about it. So writing what we know, 15 grams. And we're looking for the mass of copper. So we're going to write out our molar mass, which is 107.87. 87 grams per mole for silver. And copper is 63.55. So we're treating silver as our known and copper is our unknown. We just start with finding the moles of our known. So N is equal to little m over big M, which is equal to 15 grams divided by 107.87 grams per mole, which is equal to 0.1391 moles of silver. Now, converting from moles of silver to our moles of unknown, which is copper, we're going to go 0.1391 moles of silver. Canceling moles of silver, moles go on the bottom. And we're looking for moles of our unknown, so that goes up top, which is moles of copper. Filling in our coefficients here, 1 and 2. We're just simply dividing this by 2. So we get 0.0695, that looks like 4, sorry, 5 moles of copper. Now last step, we're looking for mass, so we need to go from moles to mass. And what we're going to do is just use N is equal to little m, or sorry, M is equal to N times big M. So 0.06955 moles times 63.55 grams per mole, decimal left, is equal to 4.4 grams of copper. All right, last example here. A teacher mixed 7.3 grams of solid sodium phosphate into solution. Students added excess of calcium nitrate to the solution. What is the name of the precipitate formed, and what mass could the students expect to find after the filtration? So, balanced chemical equation, first step. Sodium phosphate is Na3 PO4, and we dissolved it in solution, so it's aqueous. All right, it could be solid. Sorry, if we started with a solid, doesn't really matter. We're mixing it into a solution. And calcium nitrate, so NO3(2), and that's definitely in solution. And so what we're going to make is sodium nitrate, NaNO3, which we know is aqueous because everything with nitrates and sodiums are. And calcium phosphate, so Ca3PO4(2), and that's a solid. So, what mass could the students expect to find after filtration? We are looking for the mass of our precipitate here. So this is our unknown. All right, mass equals a question mark. And we started with 47.3 grams. Oh, I forgot to balance. Let's back that train up. So, looking here, I need 2 phosphates in the products, and I only have 1 here. So I'm going to add a 2 out front. Now I have 6 sodiums, so I need 6 sodium nitrates. And with that, I'm going to need 3 calcium nitrates, and that balances everybody. All right, balancing or writing out our molar masses, 163.94 grams per mole and 310.18 grams per mole. Remembering that these coefficients out front here never get considered for calculating molar mass. It's just this strictly whatever the compound is. All right, now I'm going to do this using unit analysis this time. So unit analysis is starting with our known and ending with our unknown. Okay, in the same way. So we're going to start with our 47.3 grams. From our known, we're trying to make it to moles. So what I need to do is I need to cancel grams and end with moles. Now looking at this, grams and moles in the same unit, that looks a lot like the units of our molar mass. So what I'm going to do is just fill in our molar mass there. We know that there are 163.94 grams per 1 mole. That's what we calculated the molar mass to be of our sodium phosphate. All right, so grams have canceled. And what we're going to do is now we need to cancel moles of sodium phosphate and switch to moles of calcium phosphate. Moles of Ca3PO4 2, and we are canceling moles of Na3PO4. These are, again, our mole ratio coefficients. So we're going to have a 2 and a 1. So moles of sodium phosphate cancel. And we're left now, if we pressed enter in our calculator, we'd have moles of calcium phosphate. Because that's not what we're looking for, we are looking for mass. We need to cancel moles of calcium phosphate. And what we're looking for is mass, which is calculated in grams. So we're going to fill in, because grams per mole here again, we're going to fill in our molar mass. So 310.18 grams per 1 mole of calcium phosphate. And lastly here we get our moles of calcium phosphate canceling, and we're left with mass. So mass of that, what we're going to do is calculate everything multiplied across the top. So 47.3 times 1 times 1 times 310. Press enter in your calculator. Now store that number. What you're going to do now is you're going to multiply 163.94 times 2 times 1 and press enter. And you're going to divide your top number by your bottom number. What you should get for a mass is 44.7 grams of calcium phosphate is produced. All right, you have a little bit of homework to get practicing on stoichiometry. The faster you get good at this, the better you're going to be at the rest of the unit, because it gets very repetitive. We're doing the same steps just with the different numbers and different equations. Use unit analysis if you can. Try it. It's the best option. You're going to make fewer mistakes in the long run. If you're not comfortable, go ahead and use your formulas throughout, but try and transfer over once you get confident in using your formulas and the process that you're taking.